Joe, you want to look at the table and big stuff. I think like roll people.
Okay, so let's go ahead and get started today. So as you can probably tell by looking at the board, today's topic is K-maps. Okay, K is for Carnot. And these maps, they're a pictorial way of doing reduction of Boolean equations. Okay, so it's a pictorial way to reduce base 2 equations. Now, last class, I put this handout on each table, and it shows like the different laws and axioms of base 2 algebra. And remember, we went over De Morgan. Okay? But if you take a look at these other laws, you'll see a lot of them are the same as like base 10. Like when you're foring, the order doesn't matter, just like when you're adding base 10, things like that. And you could use these laws and axioms to manually reduce Boolean equations, just like you do with base 10. You can manually factor out common terms and stuff like that, okay? But Carnot maps are a pictorial way to do the same thing. Now, out in industry, when they reduce complex Boolean equations that represent logic, they're going to use some computer program. They're not going to do it. But I feel, and a lot of other professors that teach this class feel the same way, that it's good for students to see a way to reduce Boolean equations. But for nothing else, algorithms are based on these methods. Okay? And of the two, doing it brute force and doing it a fun pictorial way, because some people do think Carnot maps are fun. They kind of look strange at first, but once you get the hang of it, it's sort of like a puzzle, if you will. Okay? So anyway, that's really what today's class is all going to be about. And then the lab, okay, lab 1, your next lab, you'll be using Carnot maps in that lab, because instead of putting into Vivado a long Boolean expression like you did in lab 0, well, you'll be able to put in a shorter version for this lab. Okay, and I'll talk about the lab 1, after we're done with the lecture here and before you start the activity. Okay, actually, I guess I put the activity in wrong order. The activity is going to be last, and I'll talk about the lab before the activity. Okay, but where I want to start before we get to Carnot maps is a couple of other things. One is I just want to make sure about this, okay, because this is a common error that students make, and that's this is not an equality, okay? Because what kind of gate is represented by this Boolean? A NAND, right? Because A and B are being ANDed together, and then the whole thing inverted, right? And that's what we call a NAND gate. Okay, this side of the equality, what's happening here? Like, what would be the logic circuitry to get this expression? Right, you're inverting A and B, and then what? Then ANDing them together, right? And from De Morgan, right? Last class, remember we talked about De Morgan's, and also it's on that sheet. By De Morgan's, we know what a NAND gate is equivalent to, right? Because one part of De Morgan's tells us that a NAND gate is equivalent to what?
Not it or nothing.
Right, it's equal to an OR gate with inverted inputs, right? Not an AND gate with inverted inputs. So the reason I bring this up is because a very common mistake, okay? You don't want to make this mistake, even if, I can understand someone might make this mistake just unintentionally when they're writing down an expression. Okay, say like in your SOP equation, you have a term like, not A, not B, C. Say that's, from a truth table, it's part of like an SOP equation. Well, that's not the same thing as doing this. Okay? That's not the same thing. Right? And I can understand that sometimes when you're writing like a long SOP equation or something, you might just, accidentally put those two bars together. But if you do, it's wrong. Okay, so you got to be really careful that when you're writing out expressions that, you don't combine bars when they're not supposed to be combined. Okay? Does that make sense to everyone?
Would go to
Say that again, please? Right, this is not logically equivalent. So yeah. Yeah, if you're writing this down from a truth table, it's no longer representing the truth table, it's representing something different. Yeah, okay. All right, the next thing is that there's two other forms of representing logic that I didn't talk about last time. And I did it on purpose just because the only time these two come up is today on your activity that's going to be on K-Maps. These two forms are on that activity handout. Okay, that's the only reason really I bring it up, because it's on the handout. You know, these forms aren't as popular as the other forms we talked about other classes. But let me just mention them because again, it's on the activity handout. One form is called compact min, and the other one's called compact max. If it's compact min, it has this sigma symbol, and then in parentheses, it'll have some numbers, okay? And the other form here has the capital pi symbol, which I don't remember. Does anyone know what this is in Greek? It's not like the product. Oh, isn't there a Greek name for it though? Because you know how you have pi, but pi is like the lowercase, right? I don't know what the uppercase pi. I think it's capital pi. Is it just uppercase pi? Oh, okay. I thought there was like another name for it. But it's just a bigger pie.
I'll take
Hey, yeah. So anyway, you've got this symbol here along with, again, numbers inside the parentheses. Well, the way you read this is that when it's a compact min, okay, with this sigma symbol, it's telling you where the ones are in a truth table. So you see, this is telling us that this is our truth table, and you know, this only goes up to 6. So we're going to say it's a free variable truth table with 0 through 7. Well, this is telling us that there's a 1 output when the inputs are 0. There's a 1 output when the input is 1. There's a 1 output when the input is 5. And there's a 1 input when the input is 6. And therefore, all the others are 0. Okay, so it just gives you where the ones are in a truth table, in a compact form. Okay, and then if you have this symbol, the numbers in parentheses is telling you where the zeros are in the truth table. Now, since this is going up to 15 and it has 8, you know, we know it's 4 variable, it can't just be 3 if it's going past 7, right? So, you know, let's say this would be telling us where the zeros are in this truth table here. So, you know, there's a 0 for F when our input is 3. There's a 0 when our input is 7. There's a 0 when we have an 8. And there's a 0 when we have 15. Sorry, I got skewed here. But anyway, all the rest would be 1. Okay, so you just fill in ones the rest of the way. Okay, so compact min tells you where the ones are. Compact max tells you where the zeros are. Well, by convention, okay, there's a couple of things that are done by convention. One is inputs are always on the left side and outputs are always on the right side. And then by convention, we do put the inputs in binary order. So, you know, just like you're counting in binary 0, 1, 2, 3, 4, 5, 6, 7. Yeah. Yeah, it just makes it easier, you know, for people to see, right? And especially when it comes to grading, I mean, like in this class, like if you mix it up, it's, you know, you're not going to make the grader happy, right? It's going to take longer if you mix it up. So please don't mix it up.
Your A, B, C, F.
This is wrong.
What is like the same, like the first, the second, the 5th, and the 6th row are all ones. It's not right there. The 7th row has a 1. Okay.
Well, it's telling us like what binary number has the 1, right? Because see, 0 is corresponding to this row that has all zeros, which is like a binary 0. And then 1. Yeah, if this bottom row was a 1, you'd see a 7 here. Like instead of 6, it would be 7, and then the 1 would be here. Okay, so yeah, like, like the top row or the first row is the 0th row. Yeah, see, in digital, we always, in fact, that's why it was lab 0 instead of lab 1. Like our first lab, I intentionally called lab 0 because in digital, we start with 0. Like you'll see eventually, like we have a 0th bit. Like the bit that's furthest to the right, which is the least significant, we call that the 0th bit, not the first bit. It's actually the bit next to it that's the first bit. But yeah, that's a good point. Yeah, sometimes that confuses people. So, okay, so that's what compact min and compact max is all about. Okay, any questions before I start talking about K-maps? Because we haven't talked about K-maps yet, but that's coming up next. All right, so let's talk about K-maps. Okay, there's 2 common K-maps. One is an 8-cell and one is a 16-cell. Okay, so I have both of them drawn up here. And each cell has a number that we call an index. So looking at the 8-cell here, the cells are numbered 0, 1, 3, 2, and 4, 5, 7, 6. And then if you look at the 16-cell, you got 0, 1, 3, 2, 4, 5, 7, 6, just like you do up there. But then it goes 12, 13, 15, 14, 8, 9, 11, 10. So the first thing you're probably wondering is because every time someone first looks at a K-map, they always ask, well, why is it 0, 1, 3, 2? Why isn't it 0, 1, 2, 3? Why is it 4, 5, 7, 6? Or 4, 5, 7, 6? Why isn't it 4, 5, 6, 7? And so on. In other words, why aren't these indexes in order? Well, the reason they're not in order is because if they were in order, you wouldn't get this property called unit distance. Okay. And what unit distance means is as I go sequentially through some binary data, it's unit distance if no more than 1 bit changes as I go through sequentially. Okay. So by going 0, 1, 3, 2, we don't have more than a 1 bit difference between any of these values, whether we're going left to right or up and down. Like for example, if you look at cell 1, right? So cell 1 would correspond to, this row of a truth table. Well, if you compare 1 to 0, right? If you compare these two, only 1 bit changes, right? Only this C bit changes, right? Also, if you compare 1 to 3, see 1 to 3, only 1 bit changes, right? Just this 1 bit. Also, if you compare 1 to 5, right here, only 1 bit changes. See, if you had 0, 1, 2, if you had 2 next to 1, so if you look at 1 and 2, more than 1 bit changes between 1 and 2. That's not unit distance. Okay? So the cells are ordered the way they are because with this order, you have unit distance for every cell. That if you look at every cell and you look to the left of it, you look to the right of it, you look down, you look up, you're just going to see a 1 bit difference. And K-maps work because of this unit distance. If you didn't have unit distance, all that I'm about to show you would not work. Okay, so it's just, an important property of K-maps that it has this unit distance relation. Okay, all right. The next thing is, look, there's an A next to this row. There's a B for these 2 columns. That's why you see this line here. That means there's B for these 2 columns. And then C means these 2 columns, right? And then down in the 16th cell, there's A for these 2 rows. There's B for these 2 rows. There's C for these 2 columns. There's D for these 2. Right? So the next thing is, well, why is there an A here? Why is there a B for these 2? Why is there a C for these 2? And so on. Okay, well, the reason why there's an A for this row that has 4, 5, 7, 6 is because look at the truth table. For 4, 5, 7, 6, A is equal to 1. Now, even though most of the time it's not written, you could write not A for this row, right? Because for this row, 0, 1, 3, 2, A is equal to 0 for all those indexes. Okay, the reason why you see B for these 2 columns is because if you look at 2, 3, 6, and 7, So 2, 3, 6, and 7, B is equal to 1 for those indexes. Okay, likewise, again, even though usually it's not shown like this, you could do this, right? Because for 0, 1, 4, and 5, 0, 1, 4, and 5, B is 0. Okay, and then C is written here because for 1, 3, 5, and 7, C is equal to 1. Okay, so that means these columns here would be not C. Does that make sense? All right, and it's the same idea for the 16 cell. For these two rows, A is 1. For these two rows, A is 0. So you could put not A here. Okay, for these two columns, C is 1. You can put not C here if you wanted to. You know, this would be not B row. This would be not B row. Not B column, not B column. Okay, does that make sense? Okay, so what do we put in these cells? The output. Exactly. We put the output that corresponds to that index. So if I'm going to transfer this truth table into this K-map, I go, okay, for index 0, which comes from our row 0, the output's a 1. Okay. For index 1, we got an output of 1. For 2, 0, 3, 0, 4, 0, 5, 1, 6, 1, 7, 0. Okay, so inside the cell is the output that goes with that index, that goes with that input. Okay, and it's the same thing for the 16 cell. You know, for this here, we have a 1 for cell 0. Probably should have wrote this. Let's see, what do we have here? We got zeros for, oh, 1's for everything. So yeah. What was throwing me off is I put this 1 a little too far down. So we're only going to have 4 zeros here. So there's going to be a 0 in the 3 cell, a 0 in the 7 cell, a 0 in the 8 cell, a 0 in the 15 cell, and then everything else would be 1s. All right. Now we're going to do a bunch of examples coming up, but before I go on, does everyone see why these are numbered 0? Well, again, the reason why these are numbered 0, 1, 3, 2, and so on is because of this unit distance. And then does everyone see, you know, why this is the A row, you know, why this is the not A row, and so on? And everybody see what we're doing to fill out the K-map? We're just taking the output that goes with that input, that index.
On the bottom one, we're at the 4x4. Why does it go from like 0, 4, 12 and then 8? I don't know if you covered that already.
Yeah, it's the same reason. It's just by doing this numbering, take any cell and go to the left, go to the right, go up and down, and you'll see there's only a 1-bit difference. That if these were in order, if I had 12, 13, 14, 15, I would have a case where I wouldn't have unit distance. That, you know, in some direction, I'm going to see more than a 1-bit change. No, and you're going to see that when we do K-maps and we do reduction, we don't do diagonal groupings. So yeah, it doesn't work diagonally. It's just up, down, sideways. Okay, but when we do groupings, we only group that way. Yeah. So yeah. So. Okay, so everybody ready now to start some examples? I mean, I'm going to tell you what the goal is and then how we do the groupings, and then we'll get to the examples. Okay, so the goal of K-maps is that you want the fewest, largest groups. Okay, we're going to group together 1s or 0s. I mean, you can either group 1s or you can group 0s, depending on, you know, what you want to get as a result. But these groups that we make, we want to get the fewest number of largest groups. Okay, that's the goal. And the reason this is the goal is because if you get the fewest number of largest groups, you're going to get the most reduced expression. You're going to get the most reduced Boolean equation. Okay? Now, when you do groupings, they can only be square or rectangular. Okay, they can't be diagonal. And let's see, what's the other thing about groupings? I think that's all. Let's see, yeah, they gotta be square or rectangular. Okay, and again, we want to get the fewest number of largest groupings. Now, like I said, we've got two K maps, 8-cell and 16-cell. With an 8-cell, if we have a grouping of just one, that's going to give us a 3-variable term. That's going to give us a term that's got 3 variables. If it's a 16-cell, and we just do it one grouping, it's going to give us a term that has 4 variables.
So this is all the pattern. 2 to the third equals 8. So the 8 cell is going to have 3 variables. And 2 to the fourth is 2.
Are you talking about like the number of groupings that I have there?
Or like the number of variables next to an 8 cell and 16 cell. There's like a pattern to it.
No, it doesn't work like that. You're going to see coming up. Okay, hang on a minute. Okay, so this is if we just have a one grouping for each of these 2 types of K-maps. Now, if we have an 8-cell and you have a grouping that has 2, like either 2 1s or 2 0s, it's going to give us a 2-variable term. With a 16-cell, it's going to give us a 3-variable. Okay, if you have an 8-cell and it's a 4 grouping, it'll give you a 1-variable term. 16-cell will give you a 2-variable term. Now, if it's an 8-cell and all cells are either 1 or 0, well then the result is either 1 or 0, right? Because if every cell is 1, my output is just 1 all the time. All right. So an 8-cell that has 8 1s, the output's just going to equal 1. Or if it has 8 0s, the output's just going to be 0. Okay, now for a 16-cell, if you have an 8 grouping, it's going to give you a 1-term variable, a 1-variable term. And then of course, 16 grouping doesn't apply to 8-cell because there's only 8 cells. And then if you have a 16-cell where all the cells are 1 or all the cells are 0, well then your output just equals 1 or 0. Okay, so you see, the larger your grouping is, the less terms or less variables you have in a term. And then the less groupings you have, the less terms you have. All right, so you see, that's why the goal is the fewest number of largest groups, right? Because the smaller the number of groups, the less terms, and the larger the groups, the less variables in a term. Does that make sense? I'm going to show you now how you do the grouping and how we get the terms and how we get the expression. But this is the goal, and this is kind of like the concept behind it. Okay, so you're ready now to do some K-maps. Now, I want you to know right up front that I didn't pick these K-maps like haphazardly. Okay, I picked all these K-maps for a reason. Okay, because each K-map brings up something kind of unique. Okay. Oh, move camera. Yes, thank you. See, I always forget. Always forget. Thank you so much. Let's see. It's my field of view here. I can move some more. Get to like, but you can move it a little bit more. I'm gonna have to move my computer. No, I think that's pretty good, probably. Yeah, there we go. All right. So we're going to look at this one first. Now, again, you can either group 1s or 0s. If I group 1s, what expression am I gonna get? What's my output if I group ones? Like what variable? K-maps come from a truth table. So when you write an expression where you took the ones, what do you put? You put this equals and you have an expression. Yeah, right. But if I group zeros, it's gonna be nada. Okay, so if we want to get the reduced expression for F, we group ones. If we want to get the reduced expression for not F, we group zeros. Okay, but we're gonna group ones to start. Okay, so we're looking at this K-map here. Oh, this is the thing I forget to write up here. I knew there was something I forget. And that's when we do these square or rectangular groupings, the groupings can only be 1, 2, 4, 8, 16. Actually, I guess I had it written. Okay. In other words, you can't have a group of 3, you can't have a group of 5.
So it came out with essentially a reduced weight expression.
A K-map is a method to get the reduced Boolean expression from a truth table. Instead of using like these identities and doing it by hand, like factoring out like you would a base 10 equation, this is sort of like a pictorial, like I said, some people think fun way of doing it. Okay. All right, so the groupings, they have to be square or rectangular, they can't be diagonal. And you can only have groupings of 1, 2, 4, 8, 16. So you can't have like groupings of 3 or 5 or 9 or something like that. So we're looking at this K-map, we're grouping ones. Right, obviously there's not 8 ones. Do we have a group of 4? No, we don't have a group of 4 ones, there's only 3 ones there. So what do we have? What's the largest group we have? 2. Yeah, which 2 are do we group? Yeah, the 0 and the 4. See, I can group these 2. Okay, 0 and 4. Now, we're going to get expression for F. And the way you get what this term is you look at what's common to that grouping. See, both these ones in this group, they're both part of not B, and they're both part of not C. A is not common, right? Because for these 2 in this group, A changes, right? Because this is in the A row, this is in the not A. So you see, A is not part of the term. So you see, the term that comes from this grouping is not B, not C. And again, the way I got that, this is the not B column, and this is the not C column. And that's what's common to that grouping. Everybody see that? Okay. Well, what do we have left? Yeah, we only have this other one over here left, and I can't group it with anything. So it's just a single grouping. So it's F equals not B, not C, or, and this is going to give us 3 variables. In fact, it's just the index, right? It's just like writing, 3 as a term. So it's going to be not A, right? Because it's in the not A column, B, C.
No, the first not B, not C were ended and not ordered together.
Oh, because we're writing an SOP. This is reduced SOP. So just like when you go from a truth table, right? It's, you look at where the ones are and you go, it's this or that that gives me the F equal 1. The only difference now is that it's in this K-map that's going to give us a reduced expression, but it's the same idea. It's going to give us an SOP. Each term is OR. Okay.
You want to do a reduced would be uninstall the same number, or just like switch the ones on the zeros.
Yeah, we're going to get to that, but yeah, you're absolutely right. See, that's a reason why you would want to get a reduced SOP for not that. Right? Because just like when I have a non-reduced, because last class we were doing non-reduced equations, right? Because we didn't even talk about B. So last class, just from the truth table, we would get a non-reduced SOP for not F, so we could then get POS for F, right, by using De Morgan's twice. Well, yeah, you're right, it's the same idea. I can use a K-map to get a reduced SOP for not F, and then again, do De Morgan's twice, and that would be my reduced POS for F, yeah. Yeah, so you're ahead of the game. We're actually gonna do that a little later. Okay, but I just want to start off basic, and we're slowly gonna get more challenging, okay? But any questions on this one? Is there, I mean, in particular, everybody see where I got this? All right, let's do the next example. Again, we're gonna group ones. Okay, now, before we go ahead and look at this any further, there's an additional thing you need to know about K-maps, and that's edges touch. So like this K-map, think of it as like it's kind of like a cylinder, and you like split it and lay it flat. You know, it's like taking a globe and making a flat map kind of thing where the edges touch. So this edge touches this edge.
But also it can pop. That is.
Well, when we get to the 16 cell, that matters, but this doesn't, I mean, that's true. All right, but yeah, I mean, that's the same as what we did here, really. But- Okay, so knowing that these edges touch, how would you group these ones? Again, you want the fewest, largest groupings.
All four of them.
Yeah, you do all four. Can you see why you do all four? Because if I did two groupings of two, I get two terms of more variables than I would with one term. You know, one four grouping term, right? Because one four grouping term is going to give me one term with only one variable, right? If I had two groupings of two, I get two terms of two variables. That's not reduced. Okay, so yeah, you would group those 0 and the 4 with the 2 and the 6. And it's a 4 grouping and it's an 8 cell, so it's only one variable is common to that 4 grouping. Do you know what it is? Not C. Right, not C, because you see, the 4 are all in the not C column. And this would just be not C. See, A is changing, B is changing, right? Because these ones over here are in the B column, these ones over here are in the not B column. Right, so that's why the B falls out. See, whatever's not common falls out. What remains is what's common. Okay, how about if I wanted not F? Since it's not F, I would look at what? The zeros. It would just be C, right? Because it'd be this 4 grouping, which is all in the C column. Okay. All right, let's move on. Let's go to this one. And again, we're going to group ones. And over here, we group zeros in. Okay, but now we're going to group ones for this one here. Okay, so what would you do first? You know, when you're doing K-maps, you should always think, you know, look for largest groupings first. You know, look for 8s. Obviously, there's no 8s. Okay, but what would you do next? Right, you get this 4 grouping again here in the middle. Right, so that's going to be F equals C. Okay, now we have this other one sticking out over here. And the reason I have this example is because you can overlap groups. So since we can overlap groups, what would you do with this one? Well, could we make it the whole bottom? No, why not? Because they got to be either 1, 2, 4, 8, or 16. But we could group it with this one. Yeah. So yeah, you do a grouping like this. Then you would make a 2 grouping like this, because if I just did a single grouping, I would get a 3 variable term. Right? By doing this 2 grouping, I get a 2 variable term. So that's more reduced. Right? See, that's, you always got to keep in your mind that, you know, the reason we're doing this is to get the most reduced expression, and to get the most reduced, it's fewest number of largest groups. Okay. All right. So this would be C, or what's common for this 2 grouping? Just B. AC? What is it? So what would the term be? AB, right, because see the two
Oh,
grouping,
right.
yeah, see, it's common to B and it's common to A. C changes, right? Because this one's in C, this one's in not. C. So it's AB. Okay, so any questions up to this point? All right, this one here, let's group zeros. Okay, so this one right here. What would you do here? Could I group these 4 zeros like this? No, because that's not a rectangle or a square, right? That's some sort of irregular shape.
I would do AC,
Okay, tell me the grouping first.
5 and 7.
Okay, so do 5, 7, okay, so just give me just a minute here. Let's write. I want to make sure I'm still in the camera. Let's write it over here. So not F, or yeah, not F, since we're grouping 0. So yeah, this 2 grouping would give me what you said.
AC,
AC, yep.
and then group 0 and 1
Okay, 0, 1.
for not B, not A, or not A.
Not A, not B, I agree. Now, also by convention, and again, to make it easier in the grader, please put your terms in alphabetical order like I'm doing. Okay, so we got,
group 0 and 2.
right, okay, good, because again, the edges touch.
For not A, not C.
Not A, C. Okay, so does everybody agree with that? Do you see a different way to do groupings? Yeah, what do you see?
You would want 5.
Right, you could see in this particular case, and that's why I had this came up. In this particular case, there's 2 correct solutions. Because I could group 1 and 5, and I would still have 2 groupings. So I would still have an expression that had 3 terms where each term was 2 variables. It would be a little bit different. Okay, so I just included this example just to point out that sometimes a K-map will give you multiple correct solutions, like multiple equally reduced expressions. Okay, and if that's the case, you just pick one of them. Now, there may be a reason sometimes when you go to put this like in an actual circuit, there may be a reason why you might choose one over the other. But I mean, academically speaking, either expression would be valid. Okay, so ready for the next one? Okay, what's different in this one?
There's dash.
There's that
Horizontal ones.
horizontal. Let's see, if we want to group 1. One's gonna be there. One. Yeah, we want to group 1 is so it agrees with my notes. All right, so what are these dashes all about? A dash here represents I don't care. It doesn't matter. Or irrelevance. Any of those words.
Really bullying it, aren't you?
So yeah, this is when we have an output where we don't care what the value is. We don't care if it's a 0. We don't care if it's a 1. It's not going to affect anything. The most common example of a practical don't care is when you have an output that's not connected. Sometimes you have a digital circuit and there'll be an output of a device or output of some part of your logic, and you're not using it. For whatever reason, you're going to see examples of that, later on in the quarter. You're going to have a design later on in the quarter where we're using a particular device made out of, logic gates, like all the circuits in this class. And we just don't need the output. Okay. So that's what I don't care. So since I don't care, whether this output or this output is a 0, 1, I can choose what it is. Right? It's sort of like a wild card. I can choose the don't care to be whatever I want, so I get the most reduced expression. Okay, so if I'm grouping ones, and I've got this K-map here with these two don't cares, what would you make these don't cares equal so you get the most reduced expression? Yeah, which one would you make a 1? Yeah, you make this a 1 and this a 0, right? Because if I make this a 1 and this a 0, I'm going to get 1 4 grouping, which is going to give me one variable term. If I made that a 0, then I'd have two groupings, right? Which is two terms of two variables. Right? I certainly don't want to make that a 1. Okay. But yeah, don't cares. You just make them equal to whatever is going to give you the most reduced expression. Okay, so this would just be F equals what? Not B. Not D, right? Because not B is the only variable common to that 4 grouping. All right, for this one, let's group zeros. So for this one here, that's got these 3 don't cares.
Make them all ones.
Why?
It could have been stuff like
Yeah, right. Everybody agree to just make all the don't care. See, I did that on purpose. I wanted to show you an example where you make all the don't cares what you're not grouping, because sometimes I think people think I got to make a don't care to what I'm grouping for, they think for some reason if they don't, it's somehow wrong. But yeah, you can have a case like this one where you want all the don't cares to be equal to what you're not grouping, because then you get the most reduced expression. Yeah. But yeah, you just make all these 1. Then the only group you have is this 1, 2 grouping. So what is this 1, 2 grouping going to give us?
Not.
Not AC, because it's in the not A, right? Both zeros of the groupings in the not A row and both in the C column. So this is not A. Okay. So is everybody good up to this? Because if you've understood everything up to this point, when we get to 16 cells, it's the same idea. Now there is one little, I won't say it's a trick, but there's one little peculiarity of 16 cell in a particular group that I'll show you one of these examples. But other than that, it's the same idea, except, because we have more cells, we have more variables, depending on the group. Like now, if you have a 2 grouping, it gives you 3 variables. 1 will give you 4 and so on. You don't have a 2 variable until you have a 4 grouping. Okay, so this is our first 16 cell right here.
0, 1, 8.
What was that?
0, 1, 8.
0, 1, 8. Oh, well, let's group 1. All right, I didn't put up here. Yeah, we're going to group 1. Let's group 1. 6. Right. Yeah, you would start with this 4 grouping, right? Because again, edges touch. Oh, okay. I thought you had a question. Okay, so yeah, we have this. This 4 grouping, and let's see, we'll write the expression here, I guess. All right, so this 4 grouping, what's common? But it's common to the B rows, and what else? And not B columns. Right, so you see this would be B not. Everybody agree with that? All right, we're not done though. We got some more ones that aren't grouped. All right, everybody agree? We would group this 1 here with the 1 next to it, right? You get a 2 grouping, because again, you can overlap groups. So that's going to give us a 3 variable term, right? Yeah. So what's that 3 variable term going to be?
Not A.
The, let's see,
Let's see, not A. E. And what'd you say? Not C, yeah,
Yeah.
it's, they're both in not C, yeah, I agree. Everybody agree? All right, but we still got this one here hanging out. Yeah, we can't group it with anything, so it's just gonna be a single grouping. So how many term, or how many variables is that gonna be for that term? Or all of them, because you're just writing a 3 in binary. So it's just gonna be, not A, not B, C, D. All right, so everybody agree with that one? All right, this one here, let's see, oh, it's like doing ones. Yeah, really keep doing ones until the last. Let's group ones again. How about grouping 6 here? Can we do that? Nope, nope, because again, it's gotta be 1, 2, 4, 8, 16.
let's start with.
Oh, how about here? We could do this. No, that's irregular, right? It's gonna be square or rectangle. So what would you do?
I do 5, 7, 13, and 15.
5, 7, and then what?
13.
Okay, so do this 4 grouping you wanna do, okay?
Yeah.
Let's see, we can write that up here. So what is that 4 grouping gonna give us? What's common to those 4? BD, right? This 4 grouping, they're both in the B row and D column, so yeah, BD.
12, 13, 15, 14.
Yeah, you could do that, right? Because again, you can overlap. Right, so we could do this row. Right, this row right here, 12, 13, 15, 14. So what's common to this 4 grouping?
A and B.
A and B, so we have 4 A, B. All right, now what are we gonna do with these 2 here? Those are the 2 that are left.
Combining with the 2 at the top.
Yep, combine it with 13 and 15. So now we have this 4 grouping here. What's common to this 4 grouping? AD. This one's actually, this K-map is common to, one of the things you'll have to do for lab 1. Like it's similar, right? It's not the same, but it's similar. Okay, let's do grouping of 1s for this one here. 1s. For this one here, we got a don't care. First of all, what would you make that don't care? Yeah, everybody agree, make it a 1, because if we make it a 1, we get a 4 grouping right in the middle. So F equals, and let's see, what's common to this 4 grouping? What was it? ED. I guess it's the same as what we did up there. Okay, here's say that again. Yeah, that's the thing I was gonna bring up that's a little peculiar with 16. Since you gotta remember, since the edges touch, right? These edges touch and also the top and bottom touch, these corners are all touching. So yeah, with the 16 cell, you can group the corners. See, this is like a 4 grouping here. You gotta kind of think of it in 3D kind of, that's kind of like a globe. But yeah, these 4 corners, you can group. So what term would that give us, these 4 corners? What's common to the 4 corners? Right, yeah, not B is common. And also not B is common. This would be not B. Okay? All right, one more. Let's group zeros for this one. What would you make the don't cares?
One, so.
Everybody agree? Yeah, because if I made any of these a zero, I end up with another term, right? That, probably combine it with this, but that'd be a whole nother term that if I make this a one, I don't even have. So when you make those ones, what's left? So this is gonna be not F. Yeah, you make this grouping, right? This column here. That's gonna give us what? Not C. Yep, not C, not D. That's what's common to that four grouping. C, D. And then what are we gonna do? Let's see, we got this zero over here.
8 and 10.
Yep, 8 and 10. And let's see, what is that gonna give us? Let's see. Say that again, A. Not B. Let's see, so, yeah, A. Not B, yeah, and not B, yeah. Now. What do you think, is the most common reason to get like a reduced expression for not F? Because what did we do last class when we weren't talking about K-maps?
Product subs. You could turn the product sub into.
Well, this is SOP, right? But if we want product of sums for F, we would, we want the reduced POS for F, we would start with the reduced SOP for not F, right? Just like last class, we weren't doing reduced equations, right? We were doing non-reduced, but if we wanted non-reduced for POS for F, we started with non-reduced SOP for not F, right? Because again, anytime you go from SOP to POS, everything inverts, right? So tell me what to write for POS here.
Or A naught.
Right? Okay. So any questions on anything we did today? Because if you understood today's lecture, then what you have to do for lab 1, you should be able to do. Because in lab 1, in fact, let me show you instructions for lab 1. Now, again, I realize that when I use the projector on the screen, the resolution isn't always the best. But what I'm putting up here is on Canvas. And let me just make one comment, because often I get emails, and believe me, I don't mind getting emails. I love getting emails from students. But a lot of times I get emails and the student couldn't save themselves a lot of time just by going on Canvas and looking what's there. Okay, so if you haven't looked on Canvas yet, especially under modules, do so, because when you look, you'll see that there's all this information, okay, including instructions for each of the labs. Right? So I would imagine everyone's gone to modules at this time because you had to turn in your lab 0, and that's where you turn it in. But anyway, if you haven't kind of browsed around, what's under modules, please do so. So if you go to modules and you click on lab 1 instructions, you'll see this document here. And in lab 1, you're going to design a locked box. It has 4 inputs, and your lockbox will open. When it opens, it means the output is a 1, right? So you can call like your output F2. And you're giving the inputs to that lockbox that unlock it, right? That make the output equal to 1. So what's the first thing you would do for this lab?
Maybe after your table.
Well, even before it came out, yeah, truth table, right? You would just put these words, right? You can take any sort of word problem, word description, and put it into a truth table. So that's the first thing you do. Put those words into a truth table. Now, we want you to come up with, well, first, it says determine the SOP and POS equations. So, you could get the non-reduced equations right from the truth table. Okay, draw a black box diagram. Okay, we talked about a black box diagram last class. What does a black box diagram tell us? When we look at a black box diagram, the purpose is what? Inputs, outputs. Yeah, it's just the main inputs and the main outputs. So how many main inputs do you have here? 4. 4. And we'll get to how many outputs you have coming up. Okay, but you're gonna have 4 inputs, and we'll talk about how many outputs coming up. But then the next thing is use a K-map to find the reduced SOP and POS. Okay, in this class, anytime you see the word reduced, reduced SOP, reduced POS, think K-map, because that's how we're reducing Boolean expressions in this class. Again, you could reduce by using these identities, these laws, but that's not what I want you to do in this class. I want you to use a K-map anytime we reduce expressions. So just like we did here in class, you're going to have to take your truth table that you come up with, put it into a K-map. Now, how many cell K-map are you going to have for this? 16. Why? Because it's a 4. Exactly. You're going to have a 16-row truth table because you got 4 inputs. So you're going to have a 16-cell K-map. How are you going to get the reduced SOP? For SOP? What are you going to group for SOP? Reduce. Yeah, you just grouped the 1. You're thinking of POS. Okay. If we want reduced SOP, we group the 1s, right? Because in my examples here, right, anytime we group 1s, it was out. If we want reduced POS, we start with, right, reduced, not a SOP, right? So, there's some examples up here where we group in the zeros, and then you go ahead and do De Morgan's twice. Now, again, you don't have to do the actual derivation like I did. You can just invert everything, change ands to ors to ands. Okay? So you're going to have your reduced SOP, POS, and now you're going to put it in Vivado. Okay? So once you have your reduced expressions, it's just you're repeating what you did for lab 0 as far as you got to make a design source. Now, lab 0, how many equations do you have for lab 0? Just have 1 equation. How many equations are you going to have here for lab 1? 1. Well, we want you to do both SOP and POS. Oh, so you're going to have 2 equations. So, when you did lab 0, you just have 1 equation, so you just have 1 assigned statement. Here you've got 2 equations right now. You're going to see there's going to be something added, next class. But for right now, you would have 2 assigned statements, 1 for your SOP, 1 for your POS. Okay, so you got your 4 inputs, but you're going to have how many outputs since you have 2 equations? 2, right? So you're going to have an output for your SOP and your output for your POS. They're going to share the same. Yes, they come from the same truth table, same everything. Like 2 of it. Yes, yeah. So lab 0, you had 3 switches because you had 3 inputs. This one, you're going to have how many switches? 4, because you got 4 inputs. Last one, you only have 1 output because you only had 1 equation. So yeah, 1 LED. But here, 2 LEDs because you got 2 outputs, SOP and POS.
And both of them should always be.
Yes. In fact, that's like the big concept behind here, right? And that even goes back to last class when you have non-reduced. Whether you have non-reduced or reduced, if you have SOP and POS coming from the same truth table, it's the same logically. So yeah, when you simulate, both your outputs should be in sync, right? They should follow your truth table. Right, and when it's on the board and you test it on the board, the LEDs should be in sync. Okay, so, did you have a question?
Yeah, I was just wondering, so why exactly do we want to do fewest large number of groups? Like, is that just to save like memory, like when you're trying to do large computations, or where was the whole purpose?
Well, yeah, if we have the fewest number of largest groups, that's gonna give us the most reduced Boolean expression, which is gonna lead to the less number of gates that we have to use, right? Because remember last class when we went from like a SOP or POS equation to the circuit diagram? Each term would give us a gate. And then, depending on how many terms we had, would determine how many inputs going to like the OR gate that ORed them all together for SOP, or the AND gate that ANDed them all together for POS. So the less terms you have, the less gates you're gonna have, and then the less, or excuse me. Yeah, the less terms, the less gates we're gonna have on like the input side of the circuit. And then also the less number of terms, the less input you're gonna have on that gate that either ORs them all together or ANDs them all together. So yeah, the reason we want the most reduced expression is because that leads to the smallest circuit, gate wise. Why do something in 12 gates when you can do it in 4? Yeah. Okay. Now, there's 2 parts to this lab, as you see. What I just described is what you can do for the first part, because we've talked about SOP, we talked about POS, we talked about how to reduce the K-map. The second part of this lab is you're going to add an additional equation, and therefore an additional output where that output is going to represent something called NOR. Okay, but we haven't talked about NOR yet. We're going to talk about that on Tuesday of next week, along with NAND. Okay, but right now you can do a large portion of this lab 1, right? Because if you were to finish part 1 before Tuesday of next week, all you would have to do after we talk about NAND and NOR on Tuesday is add like 1 more assign statement and add 1 more output. Okay. So even though you can't do the whole lab 1 yet, you can do like 90% of it. Okay. And again, when you're in Vivado, you would want to follow the same procedure as you did for lab 0. Right. In fact, what I recommend is that, actually more than a recommendation, definitely do this, that for each lab, make it its own project. Okay. So like you have a project for lab 0, make a whole new project for lab 1, okay? And then you can add in your constraints file from lab 0, so you don't start from scratch, right? Because lab 0 had 3 switches, now you're just gonna add 1 more, right? And again, lab 0 had 1 output, now you're just gonna add 1 more. Also, what I do is I use the same SIM code from a previous design I had that I know worked, and then I just edit it. So that's another thing you could do. You could do like a copy paste of your SIM code into your new project, and then just edit that, because it's all formatted the way it needs to be. But you can just make the edits. You'll have different test cases. Also, you're going to be testing a different file. You're not going to have the same file in it. But I just find that, especially when you're first learning, that if you start from scratch, you're more prone to make errors that you didn't make the first time. And it can slow you down. The other thing, the design source, that's not gonna be much more, like we said, it's just gonna be 1 more equation.
It'll be the same thing with like file, and then just not split.
Yeah, exactly. I would just add the constraints from the previous project and then just edit, because like you said, it's almost done for you, so. Yeah, it's always good to reuse files that were good previously when using Vivado. Lessens the chance that you're going to get, a problem. Right. Okay, so I think that, I wanted to make some general comments too about troubleshooting, just from some of the things that, came up during lab 0. So again, on Canvas, there's a lot of useful information. And one of the things that I want to go here, in case you haven't seen it, this document here, general publishing steps. You know, like I mentioned it on the very first day of the class, when you design something, very rarely does it work the first time you try it. So there's some general steps. Because anytime I get an email where someone's having difficulty, the first thing I ask them is, did your simulation work? Okay, again, if your simulation's not working, it's not going to work on the board. And if you're not getting a good simulation, right, your timing diagram, you know, like sometimes not everything's green, like instead of green waveforms, you might have like a blue or a red. If you have a blue or red waveform on your timing diagram, that usually either means that something's not connected right, or you didn't declare or input or output right. In fact, I had a student where I forget exactly what was blue, but it was because instead of naming, I think it was the output, instead of naming it FLC_Q, it was FLCQ, right? Just missing the underscore. Well, the software, if you don't have the name consistent throughout, it's not going to know. It's going to confuse it, okay? That's just one example. So if your simulation is not working, you shouldn't proceed to try to download to the board. Like, you don't worry about constraints until your simulation is good, okay? So if your simulation is not good, the error is either in the design source or the sim file, or it could be both, okay? So what you would want to do is look to see if you missed any red lines, because maybe you have a syntax error or something like that. And then the other thing that's really, and I know this is kind of annoying, but again, don't shoot the messenger. It's just the way it is. The compiler errors that are given, like, your error messages and your warnings, the actual text most of the time isn't helpful. It's mumbo jumbo, whatever you want to call it. But what can be helpful is a lot of times, not all the time, but a lot of times it will give you a link to where the problem is. Like, it's usually in blue, and it will have, like, sometimes what the file is. It will sometimes put what name, it has a problem with. Like, if you look in blue, it might have like what you called an output or what you called an input. So at least if you've got that link, it will take you to the portion of your code where it doesn't like something. Now, a lot of times it might not be right on that line, but it's usually close to where it takes you. Okay. The other thing is, sometimes you get an error message or a warning, and it will tell you to go to a log file, or it will tell you to type something in, which is the window underneath the TCL console. Okay. And it's always good to look at those log files or type in whatever it tells you to type in, because some of the time, again, not 100%, but some of the time, the information in those log files, or after you type in whatever it asks you to type in, is more useful. Okay, so yeah, and then the other thing is, if your simulation is good and it's failing after that, like if it's failing under implementation, or if it's failing when you go to generate a bit stream, chances are, again, it's not 100%, but chances are the problem is in constraints. Okay, and you got to be very careful with constraints when you're changing the template to whatever name you have, because you've all looked at constraints now, and you notice how there's like braces and there's like square brackets, right? And then you'll see later on there's even the regular parentheses. Well, the constraints file is very picky about those braces and those brackets. Like, if you're missing one, or if you put a brace where a square bracket's supposed to be, or vice versa, it can cause a lot of problems. In fact, previous students have made a mistake with just like a single brace, and it crashes their computer. Okay, so I just bring that up because the constraints, you've got to be very careful. Like, I wouldn't edit your constraints when you're like really tired at night. You got to be like fresh when you're doing the constraints. Okay. So anyway, those are just some of the things. So again, I don't mind getting emails. In fact, I like getting student emails, but I bring this up because you can save yourself a lot of time. Okay, because sometimes I don't see your email till the following morning. Because I'm not at my computer 24/7. I do have a light, believe it. Okay. All right. So, any questions about anything we talked about today? If not, the rest of today, work on the activity. It's on K-Maps. The answers are up there. Oh, also with the activity, there's 8K now, so I want you to do reduced SOP for all 8. And then I want you to do reduced POF just for the 4 that are on the right side. Okay, so there's a total of 12. Okay, 12 equations, 8 reduced SOP and 4 reduced POF. Okay, so what I have up in red is the reduced POF, and the rest is SOP. Okay, so work on the activity, get that done, and then once you're done with that, you got time to do lab 1. And again, when we get to the lab portion, if you want to go somewhere else, that's fine. You don't have to stay in the room once we get to the lab portion. But again, if you're gonna leave for the lab portion, make sure your group has handed in the activity before you leave, but you don't get credit if you're not physically here for the whole activity.